I'm here to give you two quick examples on how to use the method of simple poles to figure out the residue of two integrands. So we can use that to solve the integral. So as always, this is equal to 2 pi I times the residue at z equals 0. You can see that the top is holomorphic everywhere, it's entire, and the bottom has zeros at n pi, but there's only one of those in the circle of radius 1, centered at the origin. So z equals 0 is the only problem. And so if you do a quick check, you can see that the denominator has a power series, z minus z cubed over 3 plus z to the 5th over 5 factorial. That should have been 3 factorial. I can factor out, I'm not going to do anything to the top, I can factor out a z out of the denominator. And I'm left with 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial minus da da da. So I only have one z out there, and if I plug in 0 into this, I'm going to get 1 minus 0 plus 0 minus 0. So that is going to be something that's non-zero. So this has a 0 multiplicity 1 here. When you have this situation, what you can do is you can take the function that you have, take the top and evaluate it at your singularity, take the bottom, take the derivative and evaluate it at the singularity, and you're going to get your residue. This is beautiful. The residue at z equals 0 equals this thing. Well, the top evaluated at z equals 0 gives you, just plug in 0. The bottom, you have to take the derivative first, which is cosine evaluated at z equals 0, and you get negative 1 over 1 equals negative 1. So this is integral is equal to 2 pi I times negative 1 equals negative 2 pi I. There, that's one example. The second example here, let's write into the DZs. Second example is a little more complicated, but same idea. Notice that the top is entire. The top is holomorphic. So this is going to be equal to 2 pi I times, we'll see that the only residue is again at 0. Notice that e to the z equals 1 plus z squared over 2 factorial plus z cubed over 3 factorial minus 1 is just going to give you z plus z squared over 2 factorial plus z cubed over 3 factorial plus da 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 equals, you can factor out a single z out of the power series here. And then I get something. So this is a 0 of multiplicity 1, and this does not have a root at z equals 0. So now I know I can apply the rule. The top is holomorphic everywhere in here, and the bottom just has a single 0 there. So what I can do is I can say that the residue at z equals 0 equals, well, I'm just going to take the top, plus 7 plus z plus e to the times e to the z. Take the bottom, e to the z minus 1. I'm going to evaluate the top at z equals 0, and I'm going to take the derivative of the bottom and evaluate it at z equals 0. And this is equal to 0, 0, 7, 0. So this just equals 7, and the derivative here is equal to e to the z, evaluate it at z equals 0. So I get 7. So I just plug this in here, and I get 14 pi I. So if you have a simple 0 on the denominator and the top is holomorphic everywhere, this is a really slick way of figuring out what the residue is, which allows you to figure out the integral.